Hello friends, and welcome to our video lecture on topic R3.1 Proton Transfer Reactions. We're going to look at acids and bases and pH. Our guiding question today: what happens when protons are transferred? Here are all of our understandings. If you want to pause the video and read them, feel free to do so. Otherwise, here are our objectives. We're going to define acid and base. We're going to talk about this super cool thing called hydronium. We're going to explain conjugate acid-base pairs, more vocabulary, amphoteric, amphiprotic, and Zwitterion. We're going to perform some calculations involving pH and Kw, which is the ionic product of water. Consider grabbing your calculator if it's not already nearby. We're going to talk about properties of acids and bases, and then look at lots of reactions and predict the products of those reactions involving acids and bases. But first, as promised, our definitions of acids and bases, which, as with most of science, have changed over time. One of our first definitions of acids and bases came from Robert Boyle, an Irish chemist in the 17th century. He said that acids taste sour, react with metals, neutralize bases, and turn litmus red, whereas our bases feel slippery. They neutralize acids. They turn litmus blue. This was a good definition in terms of describing properties of acids and bases, but it didn't really say anything about how or why. And then Arrhenius came along in 1884, and he redefined acids and bases as this. Acids are substances that in water dissociate to produce hydrogen ions. So hydrochloric acid is going to pop apart in water to produce H pluses and Cl minuses. Those H pluses, those hydrogen ions, we can also call them protons, are what make acids acids. And then bases are going to also dissociate. They dissociate in water to produce hydroxide polyatomic ions. These hydroxide ions are what give bases their base properties. This is pretty much still the definition that we use today, except that it has a small limitation, and that limitation is ammonia. We know that ammonia, NH3, is a base. Where's its hydroxide? It doesn't have one. And so ammonia is kind of excluded from the Arrhenius definition of a base. So Brønsted Lowry in 1923 simply expanded Arrhenius' definition a little bit to say that instead of dissociating to produce hydroxide polyatomic ions, what bases can do is add hydrogen ions, those protons, to them. When ammonia does this, we end up with the polyatomic ion ammonium. Acids, therefore, will donate or lose those hydrogen ions, which is pretty much what Arrhenius said. We're going to dissociate to produce hydrogen ions. Our acids are going to be proton donors, remove those H pluses, whereas our bases are going to be proton acceptors. They're going to accept or take on those hydrogen ions. I've been using this word dissociation quite a bit already. To dissociate is simply to pop apart. When we look at hydrochloric acid in water, it is going to dissociate. The H plus and the Cl minuses are going to pop apart. What's kind of fun is that in water, often those protons are going to get stuck to some water molecules to produce this thing, H3O plus 1, which we're going to call hydronium. Now, ammonia doesn't dissociate. It doesn't pop apart into pieces the way that this acid or a base like sodium hydroxide would dissociate. So no dissociation here. Instead, what's going to happen is simply ionization. We also have ionization here. We've produced quite a few ions when that hydrochloric acid molecule dissociated in water. Here, I have only ionization, not dissociation. Ammonia didn't pop apart, but you know what it did do? It did turn into an ion. Ionization. And a quick little comment on alkali versus base. Most of the time we're going to use this word base to describe our bases, like sodium hydroxide. But sodium hydroxide is also an alkali. Alkalis are water-soluble bases, whereas bases are all substances with basic properties. All alkalis are bases, but not all bases are alkali. So this one is sodium hydroxide. It is an alkali. It is a pretty strong base. Sodium oxide is a base, but it's not an alkali. It's not a water-soluble base. However, you know what happens when this guy reacts with water? We end up with, you guessed it, sodium hydroxide, which is both an alkali and a base. So just little bits of differences, alkali versus base. All alkalis are also bases, but there are some bases that are not alkalis. It's kind of like dogs and mammals. All dogs are mammals, but not all mammals are dogs. What's pretty cool about our acids and bases is that they come in these things called conjugate pairs. Let's look again at hydrogen chloride in water. It's going to dissociate into its H plus and its Cl minus. That H plus is going to bind to a water molecule and we're going to get hydronium. What's left over is that chloride anion by itself. There it is. This guy is donating that hydrogen ion. That makes it an acid. This guy, the water molecule, is accepting that hydrogen ion from the hydrogen chloride. That makes it a base. What's super cool is that water turns into hydronium when it accepts that hydrogen ion, that proton. So what can happen is that this guy can actually donate that extra proton back to chloride. So it can actually take one of those extra hydrogen ions and give it back to chloride. It becomes a proton donor. You know what that makes it? It makes it an acid. Proton donors are acids. When chloride accepts that extra proton from that hydronium ion, it's a proton acceptor. That makes it a base. Notice that water and hydronium are almost the same molecule. The only difference is that this guy has one hydrogen ion more. That makes it the acid to the base in this acid-base conjugate pair. Look also at hydrogen chloride and the chloride anion. They're almost the same with the exception of this guy has one hydrogen more. That makes it the acid to the base in this conjugate pair. Let's do the same thing for ammonia in water. So what we're going to see here is ammonia is going to accept a hydrogen ion from water. Water has two hydrogens right here, only one over here. That means that one of those hydrogens was given to ammonia, and this is how ammonia became ammonium. Since ammonia is accepting a proton from water, it is the base. And since water is donating a hydrogen ion, it's the acid. But what can happen is that this ammonium, with its extra hydrogen, can give it back to hydroxide. That makes hydroxide a proton acceptor. It's a base. And ammonium is the acid because it is the proton donor. So now we have this acid-base pair. They're almost the same except that water has one hydrogen ion more. And then we also have this acid-base pair, again, almost the same except that ammonium has one hydrogen more than does ammonia. So we have these conjugate acid-base pairs where our acid is going to have one hydrogen ion more than the base. The rest of them will be the same. Take a moment and be amazed and astounded by the fact that I called water here a base, and I called water here an acid. So which one is it? Is water an acid or a base or both? And the prize goes to both. Water is both an acid and a base, and so we call it amphoteric. It displays properties of both acids and bases. This prefix amph means both. Like amphibians live both on land and in water. Amphoteric means displaying properties of both acids and bases. What's pretty cool about water is that it is also amphiprotic. Again, both, but now I have this protic thing, which is all about protons or hydrogen ions. Water can give away, be a proton donor, and end up with hydroxide. but water can also accept a proton, and we will end up with hydronium. So because water can be both an acid and a base, we call it amphoteric. Because it can both donate and accept protons, we're going to call it amphiprotic. It's both amphoteric and amphiprotic. Let's talk about aluminum oxide. Remember a long time ago we talked about periodic trends, and our metal oxides in water produce bases. Our non-metal oxides in water produce acids. But in the middle, between the metals and the non-metals, we had aluminum, and it was amphoteric. It can act both like an acid and a base. So if I take aluminum oxide and I add it to an acid like hydrochloric acid, it can neutralize that acid, and we end up with water instead of an acid. And if I put aluminum oxide in a base like sodium hydroxide, it can neutralize the base, and once again we end up with water. You know what neutralize acids? Bases. You know what neutralize bases? Acids. And so a substance like aluminum oxide is amphoteric because it can act both like an acid and a base. However, it is not amphiprotic. Clearly, it has no hydrogen ions to donate. Another super cool thing that is amphiprotic and amphoteric are Zwitterions. I've also heard this pronounced Zwitterions, but I learned it Zwitterions, so that's what I'm going to say. But if your teacher says Zwitterions, also correct. So these Zwitterions, amino acids, we'll do a little bit of biology review here. Amino acids are the building blocks of proteins. They have this super cool amino group, and they've got this carboxyl group. What happens is the hydrogen that we usually draw in the carboxyl group on the carboxylic acid side of the amino acid can actually pop off and stick itself to the amino group. And so we're going to end up with this thing that has charges, a charge here and a charge here, but those charges are equal. So there's a net zero charge, equal positives and negatives. That makes it a Zwitterion. What's pretty cool about our Zwitterions is that if we put them in low pH environments, so add an acid to it, there's a higher concentration of those hydrogen ions, which means that we can stick a hydrogen ion onto that oxygen, but also keep one on the amino group. And so it can be a proton acceptor. It can act like a base. But wait, if it's in a high pH environment, so lots of hydroxide, or hydroxide is negative, not positive, sorry. Lots of hydroxide or a very, very low hydrogen ion concentration, what happens is this. It will give away, donate that extra H+. That makes it an acid. So it is also amphoteric and amphiprotic because it can both accept and donate protons depending on what the environment is. It also acts as an acid and as a base. We can do some super cool math with our hydrogen ion concentrations to calculate pH. The formula for pH is given to us in section 1 of our data booklet, some relevant equations. Almost all the way down to the bottom, we're going to use the pH is equal to the negative log base 10. We also call this the common log of the hydronium ion concentration. It can also be the hydrogen ion concentration. We use these interchangeably. We're going to assume that if there's an H+ in a solution, it's going to stick to water to make that hydronium ion. So let's say that I've got a hydrogen ion concentration of 0.0001 moles per cubic decimeter. To find the pH, pH is going to be the negative log base 10, the negative common log of 0.0001. When I'm trying to find logarithms, what I'm doing is what is the exponent on the base? Since it's common log base 10, I'm trying to figure out 10 to what power is equal to 0.0001. Well, let's do some decimal jumpings. 1, 2, 3, 4. So that means that 10 to the negative 4 is equal to 0.0001. So when I say what is the common log of 10 to the negative 4, you're going to tell me that the exponent on the 10 is negative 4. So negative log, the negative common log of 10 to the negative 4 is negative 4. but it's negative, so negative, negative ends up with a positive 4. The pH is 4. What if I have a hydrogen ion concentration? Remember that these square parentheses tell us a shortcut for concentration. The concentration of the hydrogen ion is now 0.01 moles per cubic decimeter. pH is going to be the negative log of that concentration, 0.01, which in scientific notation is 10 to the negative 2. Negative common log means what's the exponent on the 10? The exponent's negative 2, but I want the negative 2. My pH is going to be 2. Sometimes we learn, or we just assume rather, that pH goes from 1 to 14. Friends, what if I have a hydrogen ion concentration of 1 mole per cubic decimeter? We absolutely have this solution in the lab. What's the pH of a concentration of 1 mole per cubic decimeter? Negative log of 1. Well, 10 to what power is equal to 1? 10 to the 0 power is equal to 1, and so our pH is 0. What madness! Is that as low as it goes? Oh, you know that hydrochloric acid that we have sitting in the fume hood that we used to make our dilutions in the lab? It had a concentration of 12 moles per cubic decimeter. What is the pH of something that has a concentration of 12 molar? Negative common log of 12. I can't do that one in my head. I'm going to plug it into the calculator. Negative log of 12 is, what? Negative 1.08. We can have negative pHs. These don't really exist in nature because they are so highly reactive that they're going to react with stuff and not be that strong of an acid. But in the lab, we absolutely can isolate these solutions and have negative pHs. And we can have pHs of over 14 if we have very, very strong concentrated bases. So pH, negative common log, negative log base 10 of our hydrogen ion or hydronium concentrations. Just under our equation to find pH in section 1 of the data booklet is this thing called Kw. Kw is also given to us in section 2 of the data booklet. So it's in 1 and in 2. In 2, it's down here, Kw. The ionic product constant for water at 298.15 Kelvin, which is just about 25 degrees Celsius, is equal to 1 times 10 to the negative 14. What even is Kw? Kw is the ionic product of water. So what happens to water is that sometimes it pops apart. It can dissociate. And so this water molecule could pop apart into hydrogen and hydroxide. The hydrogen can stick to another water molecule and we'll end up with the hydronium ion. And then that hydroxide guy is left to be hydroxide. If I take the product, multiply, if I take the product of the concentrations of those two ions, I'm going to get the ionic product. Get it? Ions. Multiply is the product. So if I take the concentration of the hydroxide ion and I multiply it by the concentration of the hydronium ion, which we can also call just the hydrogen ion, we're going to get this thing called Kw. Kw has different values for different temperatures. We just need to know that at 25 Celsius or 298.15 Kelvin, we're going to have 1 times 10 to the negative 14. What's pretty cool is because we have equal amounts of hydrogens and hydroxides, because each one water is going to pop apart into one hydrogen and one hydroxide, we know that these two guys are equal to each other. So if I have OH minus times H plus is equal to 10 to the negative 14, I know that these guys are equal to each other, so I can call each of them x. So when I do x times x, I get x squared. X squared is equal to 10 to the negative 14. To find x, we're going to take the square root of each of these. What times what is 10 to the negative 14? Well, that would be 10 to the negative 7. So at 25 Celsius or 298.15 Kelvin, the hydroxide concentration in a solution of pure water is going to be 10 to the negative 7 moles per cubic decimeter. And then the hydronium ion's concentration is also going to be 10 to the negative 7 moles per cubic decimeter, because 10 to the negative 7 times 10 to the negative 7 is equal to 10 to the negative 14. But wait. To find the pH, we're going to take the negative log of the hydrogen ion concentration. which is 10 to the negative 7, the negative log of 10 to the negative 7. What's the exponent on the 10? Oh yeah, the pH of water is 7. We can use Kw to figure out ion concentrations of solutions, aqueous solutions that aren't pure water. It's pretty cool. So let's say that I've got this acid solution, hydrochloric acid, that has a concentration of 0.01 moles per cubic decimeter. And I actually want to figure out how much hydroxide ions are left from the water that is dissociating. So we know that an aqueous solution has water, and we know that sometimes that water can dissociate into hydrogen ions and hydroxide ions. We know that our hydrogen chloride in water is going to dissociate into H pluses and Cl minuses. Sometimes that higher concentration of H plus from the acid is going to bind to the OH minus. I shouldn't say sometimes, almost all the time. Those hydrogen ions are going to go and find our hydroxide ions and then form more water, reducing the amount of hydroxide that's going to be consumed by the extra hydrogens from the acid. So we can actually figure out how much hydroxide is left after the hydrogen ions from the acid are consuming them. So what we can do is, again, use our Kw formula and constant. So Kw is going to equal the hydrogen ion concentration times the hydroxide ion concentration. That product at 25 Celsius or 298 Kelvin is going to be 10 to the negative 14. So my hydrogen ion concentration, the great majority of my hydrogen ions are coming from the acid. So 0.01 as a scientific notation little piece is 10 to the negative 2. So I'm going to use the acid's hydrogen ion concentration as my hydrogen ion concentration. So 10 to the negative 2 or 0.01. But you're thinking, wait, there should be some hydrogen ions coming from the water as well. You're right. The hydrogen ion concentration of the water, because of Kw, is 10 to the negative 7, which is equal to 0.0000001. And we're going to add to that 0.010. So our hydrogen ion concentration technically is 0.010001. But when I do sig figs, that guy goes away. So we basically just have what we have from the acid. The contribution of the hydrogen ions from the water is negligible, so we're just going to round to the concentration of the acid. So 0.01 mole per cubic decimeter hydrogen ion concentration times the hydroxide ion concentration that we're trying to figure out here is going to be equal to 10 to the negative 14. So how do I solve here? I have 10 to the negative 2 times x is equal to 10 to the negative 14. Divide both sides by 10 to the negative 2. That's going to leave us with an x equals 10 to the negative 14 divided by 10 to the negative 2. When we divide with the same base, different exponents, we subtract our exponents. So negative 14 minus negative 2 is going to give us negative 12. So this means that the hydrogen ion concentration is equal to 10 to the negative 12 moles per cubic decimeter. This makes so much sense because we should have in an acid a whole lot more hydrogen ion than we have hydroxide ion. If I had a base, my hydroxide concentration would be a whole lot higher than my hydrogen ion concentration. And if we have water, that's when they're equal. So we've been talking about these acids that are solutions that donate protons, but friends, not all protons are donatable, so be careful. This acid is chlorous acid. It is HClO2. There's the Cl. Those red guys are the two oxygens, and then here's our hydrogen. This hydrogen is what we call exchangeable. It can pop off. It can dissociate. So we have an exchangeable hydrogen. This makes this guy a pretty good acid. Over here we have another acid. This one is ethanoic acid. Ethanoic acid. This is the acid that we find in vinegar. It's got a hydrogen, it's got a hydrogen, it's got another one and another one. Does that mean that it can donate 4 hydrogens? No, only this one is donatable. Only this one is exchangeable. These guys are non-exchangeable, and so they are not going to contribute to this guy being an acid. This hydrogen is exchangeable most of the time when we have our organic acids like ethanoic acid. The hydrogen that is bound to the oxygen is the one that is exchangeable. The bonds between the carbons and the hydrogens do not allow for these hydrogens to be donated. These are non-exchangeable hydrogens. So the acidic part of ethanoic acid is only this donatable, exchangeable hydrogen. Not all hydrogens are exchangeable. Not all hydrogens can dissociate from a molecule. Here we have hydrochloric acid. Does it have an exchangeable hydrogen? It sure does. It has that one right there. Here we have sulfuric acid, H2SO4. Does it have an exchangeable hydrogen? Look, I've got a hydrogen bound to an oxygen. That makes it exchangeable. But wait, I have another hydrogen bound to an oxygen. This one is also exchangeable. It has 2 exchangeable protons. We are going to call it a diprotic acid. Going back to hydrochloric acid, it only had 1. Can you guess what we call it? It's a monoprotic acid. 1 proton. Ooh, how about phosphoric acid? How many exchangeable hydrogens are there? There's 1, there's 2, there's 3. You guessed it. It's a triprotic acid. Hydrochloric acid is one of our favorite acid examples because it is strong. What it means to be a strong acid is that it completely dissociates in water. So when I have hydrogen chloride in water, pretty much every single unit of hydrogen chloride is going to dissociate, pop apart into Cl minuses and H pluses. There are going to be maybe 1 out of a bazillion. I know that's not a real number, but imagine. Very, 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 very few hydrogens and chlorides are going to get stuck together. Most of them, pretty much all of them, are going to pop apart. And so we say that hydrogen chloride is strong acid because it completely dissociates in water so many hydrogen ions. That's not true for all acids. Some acids are weak. Going back to our ethanoic acid, this is the acid that's in vinegar. This guy is a weak acid because it does not completely dissociate. And we're not even talking about our non-exchangeable hydrogens. We're just focused on this one guy. So this hydrogen is exchangeable. It can pop off. It just doesn't very often. When we get to equilibrium, we're going to do a little bit more of this math. But for now, I'm going to say that the equilibrium constant for this acid equilibrium constant is just about 2 times 10 to the negative 5. That's a 0.00002. What that means for this acid is that only 2 out of tens, hundreds, thousands, 10,000, 100,000, only 2 out of every 100,000 of these molecules are actually going to lose their hydrogens. So most of the time, that hydrogen is going to stay stuck to its oxygen. Only 2 out of 100,000 times is that hydrogen actually going to pop off. It's still an acid. It can still donate protons. It just doesn't do it very often. For both strong and weak acids, we can have concentrated and dilute versions. I can have highly concentrated strong hydrochloric acid. We can talk about 12 moles per cubic decimeter HCl. I can also have 12 moles per cubic decimeter ethanoic acid, C2H4O2. But wait, there's more. I can have dilute versions of a strong acid like hydrochloric acid. We diluted hydrochloric acid in lab. We can have 0.0001 moles per cubic decimeter hydrochloric acid solution. That's dilute, but it's still strong. We can also have dilute weak acid. We can have 0.0001 moles per cubic decimeter ethanoic acid. So be careful with this vocabulary. Strong completely dissociates. Concentrated, the molarity, that solution concentration is high. A lot of moles dissolved in the solution. Weak acids only partially dissociate. Completely dissociate, only partially dissociate. But we can have concentrated versions of them, but we're still not going to have a lot of hydrogen ions popping off. Good? Good. Again, our strong acids are those that completely dissociate in water to produce all of the hydrogen ions. If we look at binary acids are those that have just two elements, hydrogen and something else like hydrochloric acid or hydrosulfuric acid. As we go down group 17, the halogens, or down any one of these groups, we're going to have bigger and bigger atoms, which means that the bonds are weaker, which means that it is easier for the hydrogen ions to pop off. Iodine is quite large. The hydrogen is not bound to it as strongly as hydrogen is bound to fluorine. That means it's pretty easy for the hydrogen to dissociate from the iodine. This is going to be a stronger acid. Hydrogen fluoride, that hydrogen holds on to fluorine pretty closely. Fluorine is super electronegative. It is small. The bond is quite strong. That means that fewer of those hydrogen ions are going to dissociate. That's going to make this a pretty weak acid. As we go across a period, getting closer and closer to the halogens, we're going to also have stronger and stronger acids. This guy is so weak, it's a base. This guy is an acid, but it's a pretty weak acid. So going this way, we're getting stronger. In terms of acids, going this way, going down the groups, we're getting stronger. Across the periods, down the groups, getting stronger and stronger acids when we're talking about our binary acids, just two elements, hydrogen and one other. If we're talking about our oxoacids, these are guys formed from polyatomic ions and hydrogen. They're going to always have some oxygen in them. Then we're going to look at oxidation state instead. So oxygen is always going to have a -2 and hydrogen is going to be a +1. What is the oxidation state of the nitrogen in this acid, nitric acid? Well, I've got -2 times 3 is -6. We've got a +1. That means that nitrogen here has to be a +5. Let's look at the same thing in nitrous acid. I've got a -2 for the oxygen times 2 is -4. We still have a +1 for the hydrogen. +1, -4. What does the nitrogen have to be to balance out this molecule? Well, now it's going to be a +3. The more positive the oxidation state, the stronger the acid. The closer to 0, the lower that oxidation state, the weaker the acid. Let's do the same thing for sulfuric acid and sulfurous acid. Oxygen is still a -2. -2 times 4 is -8. I've got a +1 for the hydrogen. There's 2 of them. That's +2. What does sulfur have to be? It needs to be a +6 in sulfurous acid. -2 times 3 is -6. +1 times 2 is +2. What does this sulfur have to be? It has to be a +4 to balance out the charges in this molecule. Which one of these two is the stronger of the acids? Sulfuric acid is stronger because its oxidation state, the oxidation state of the sulfur, is higher. Good? Quick nomenclature review. Remember that if the polyatomic ion ends in -ate, like sulfate, then the acid is going to be sulfuric acid. If our polyatomic ion ends in -ite, SO3 2- is sulfite, then the acid's going to end in -us. This is sulfurous acid. Nitrate, nitric acid, nitrite, nitrous acid. A few slides ago, we talked about how sulfuric acid has 2 hydrogens to give it away. That makes it diprotic. Any of our acids that have more than 1 proton, we can also call polyprotic. Polyprotic acids are those that have more than 1 proton to donate. What's pretty cool is that they can continue to donate those protons. So here we have our sulfuric acid. It can give away one of its hydrogens, and we're going to end up with HSO4-1. This guy can also give away that second hydrogen, and we're left with just that sulfate polyatomic ion. What's interesting is that this acid, it's an acid, it's donating a proton, is strong. Whereas this guy, what's left over after one of those hydrogen ions pops off, it doesn't give away its second hydrogen quite as easily as that first one was given away. So this second dissociation is going to be a little bit weaker than the first. We've had so many words about acids. Let's talk about properties of bases for just a little bit. Some of our bases follow Arrhenius' definition of dissociating in water to produce hydroxide. Sodium hydroxide is a very strong base. It is going to completely dissociate into hydrogen ions and hydroxide ions in water. It's what we call an ionic hydroxide because there's an ionic bond between the sodium and the hydroxide. Completely dissociates, super strong base. Calcium hydroxide is also an ionic hydroxide. There is an ionic bond between the calcium and the hydroxide. It actually doesn't dissolve in water all that great, but we are still going to get those hydroxide polyatomic ions. It is also a strong base. It's an ionic hydroxide. You might be thinking, aha, it's another metal nonmetal. It's another ionic hydroxide. Nope. I'm going to throw a little bit of a plot twist in here. The electronegativity differences between these guys actually result in not an ionic bond. There is not a big enough difference here for it to be ionic. It's a covalent hydroxide. What madness! It is barely soluble in water, and so we don't get a bunch of hydroxides popping off. This is going to be a very, very weak base. And then, of course, we have ammonia, which doesn't even follow the Arrhenius rule. We had to add the Brønsted-Lowry rule about being a proton acceptor. And ammonium will accept some protons, or ammonia accepts some protons to become ammonium, but it doesn't accept a bunch of them. And so it is also a weak base. Remember that our conjugate acid-base pairs are these pairs of acids and bases where the acid has one hydrogen more than the base, but otherwise they look the same. Hydrogen chloride and chloride are acid-base pairs. This guy has one hydrogen more, that makes it the acid. This one has one hydrogen fewer, that makes it the base. Otherwise they look the same. What's pretty cool about our acid-base pairs is that they come in strong and weak. If you have a strong conjugate acid, its conjugate base is going to be weak. This guy is really good at popping off those hydrogens. This guy is not so good at taking them back because it wants to pop off, not pop on. This one is our base and this one is our acid. This acid has one hydrogen more. It has 3. This one has one hydrogen fewer. That makes it the base. Hydronium is a strong acid. Water is a weak base. Hydronium is really good at giving away that hydrogen ion. Water is not so good at wanting to take it. So again, we're going to have one strong and one weak in each pair. If I have a strong conjugate acid, its conjugate base is weak. If I have a weak base, its conjugate acid is going to be strong. Here I have a weak base. Can you find its conjugate acid? Look for one hydrogen more. That's going to be ammonium. Ammonium is an acid, and because ammonia is weak, ammonium is strong. It's a strong acid. It's going to very easily donate that hydrogen. Here we have our acid, and here we have our base. This base is pretty strong. That means that this guy is going to be pretty weak. Conjugate acid-base pairs come in one strong and one weak. We talked about our polyprotic acids. The bases follow a similar kind of pattern. So we can have more than one proton in these molecules, and sometimes they can act as bases. Sulfate polyatomic ion with 0 protons is the strongest of our bases. It's the best at adding protons. When it adds one proton and becomes this hydrogen sulfate ion, it's not as good as at accepting those protons, and so this one is a little bit weaker of a base than was that sulfate polyatomic ion. This guy will take on some hydrogen ions, but not as readily, not as well as does sulfate. Let's talk about some of the chemical reactions that acids and bases are involved in. If we have a metal and an acid, like magnesium and hydrochloric acid, we're going to end up with some kind of salt. In this case, it happens to be magnesium chloride and some hydrogen gas. It's a gas. This salt is dissolvable in water, so we're going to call it aqueous. To balance this, I simply need 2 hydrogen chlorides. Sometimes we like to take our acid-base reactions and write some ionic equations. We can talk about a total ionic equation where I pretty much just rewrite this with everything's charges. So I've got Mg, its charge is a 0. We've got 2 hydrogen ions that have a +1 charge. We've got 2 chloride ions that have -1 charge. We end up with magnesium with a +2 charge. We've got 2 chlorides that still have a negative charge. Now I've got this hydrogen gas molecule that is neutrally charged. So I can take my total ionic equation and I can write what we call a net ionic equation, where I get rid of things that do not change charge. Notice that my chloride and my chlorides don't change, they stay the same. We call these guys spectator ions because they just kind of sit and watch everybody else's charges change. When I write a net ionic equation, we do not include the spectator ions. What's left? We still have our magnesium, we still have our 2 hydrogen ions. We end up with magnesium that has a +2 charge and our hydrogen gas molecule. This should feel very much like all the redox stuff that we did. Net ionic equation, total ionic equation. What if I have a weaker acid? This is our ethanoic acid, an organic acid, and a metal. Similar idea. We're going to have another single replacement reaction. Our sodium and that exchangeable hydrogen are going to trade places. We're going to end up with, once again, some hydrogen gas. And now we're going to put the sodium on the rest of that ethanoic acid. We're now going to call it an acetate polyatomic ion. So we end up with sodium acetate, which is aqueous. And this is our salt. Magnesium chloride, also a salt. These, again, are just ionic compounds. What if I take a metal oxide and I add it to an acid? What are we going to get? Well, now instead of a single replacement reaction, we have a double replacement reaction. The Mg is going to pop off of the O and pop onto the chloride. The hydrogen is going to pop off of the chloride and pop onto the O. We're going to end up with, once again, a salt. Here's our magnesium chloride. It's aqueous. It's going to dissolve in the water. And what do we have left? An O and 2 H's. Oh, that's water. So we make some water and a salt. What if instead of a metal, we have a metal carbonate or a metal hydrogen carbonate? This is also called bicarbonate. So these are pretty fun. What happens is another double replacement reaction. The sodiums and the hydrogens are going to change places. Sodium's going to pop onto the chlorine and the hydrogen's going to pop onto the carbonate. That's going to give us NaCl and H2CO3. Carbonate's charge is -2, so it needs 2 hydrogens to balance out. We're going to need 2 hydrochloric acids. We're going to end up making 2 of those salt molecules. What's crazy cool about this is that this molecule, this is carbonic acid, it is not a stable molecule. It likes to spontaneously decompose into water and carbon dioxide. When we add baking soda to vinegar and we get our super fun bubbles, this is what's happening. We made some carbonic acid for just an instant. It decomposed into water and carbon dioxide. When you write a balanced equation showing the reaction between an acid and a carbonate, do not leave carbonic acid in your formula, in your balanced equation. What you need to write instead is sodium carbonate and hydrochloric acid produce salt and water and carbon dioxide. This is the correct answer. This is not the correct answer. Same thing happens with our hydrogen carbonate. So we're going to have, again, double replacement reaction. We're going to end up with NaCl, and that H with that H makes our H2CO3 carbonic acid. Once again, it's going to spontaneously decompose. So we do not leave it in our equation. The better thing to write is that we make our salt and water and carbon dioxide. That's a gas. That's a liquid. That one's aqueous. Last idea of the day, my friends. We are so close to being done. All those reactions that we just looked at, we can go backwards and figure out from this salt, this ionic compound, what our parent acid might have been. We're basically just going to take this guy apart and turn it into an acid and a base. So here's my metal lithium. I'm going to make it a base by adding hydroxide. Here's my sulfate polyatomic ion. I'm going to make it an acid by giving it some hydrogen ions. And when we combine these two together, you know what we're going to make? We're going to make exactly that lithium sulfate and some water, 2 waters in fact. So if I'm looking for the parent acid of some salt, basically we just throw some hydrogens onto the anion. And my friends, we have come to the end of this video lecture. We talked about transferring protons. We defined acid and base. We talked about hydronium, that H3O positive polyatomic ion. We talked about conjugate acid-base pairs. The acid is always going to have 1 hydrogen more than does its base. Amphoteric acts like an acid and a base. Amphiprotic can donate and accept protons. Zwitterions can be an acid or a base depending on the environment that it's in. pH is the negative log of the hydrogen ion concentration, and Kw, the ionic product of water, is equal to 10 to the negative 14 at 25 degrees Celsius. We talked about lots of properties of acids and of bases, and then we looked at all those reactions involving acids and bases. Great work today, my friends.